the Lewis electron pair approach can be used to predict the number and types of the bonds between the atoms in a substance, and it indicates which atoms have a lone pairs of electrons. This approach gives no information about the actual arrangement of atoms in a space. However, we continue our discussion of structure and bonding by introducing the valence shell electron pair repulsion model, which is pronounced as VSEPR, and which can be used to predict the shapes of many molecules and polyatomic ions. By keeping all these things in our mind, however, that the VSEPR model, like any model, is a limited representation of reality. The model provides no information about bond lengths or the presence of multiple bonds. Now we are talking about the VSEPR model. The VSEPR model can predict the structure of nearly any molecule or a polyatomic ion in which the central atom is a non-metal. You can see on your screen, as well as the structures of many molecules and polyatomic ions with a central metal atom. The premise of the VSEPR theory is that electron pairs located in a bonds and lone pairs repel each other and will therefore adopt the geometry that places electron pairs as far apart from each other as possible. This theory is very simplistic and does not account for the subtitles of orbital interactions that influence molecular shapes. However, the simple VSEPR counting procedure accurately predicts the three-dimensional structures of a large number of compounds which cannot be predicted using the Lewis electron pair approach. Here you can see in the diagrams, that is, there is a linear shape, there is a triangular shape, there is a pyramidal shape, there is a tetrahedral shape, and we can say that we can use the VSEPR model to predict the geometry of most polyatomic molecules and ions by focusing only on the number of electron pairs around the central atom, ignoring all other valence electrons present. And according to this model, valence electrons in the Lewis structure form groups which may consist of a single bond, double bond, triple bond, a lone pair of electrons, or even a single unpaired electron, which in the VSEPR model is counted as a lone pair, because electrons repel each other electrostatically. The most stable arrangement of electron or its groups, that is, the one with the lowest energy, is the one that minimizes the repulsions. Groups are positioned around the central atom in a way that produces the molecular structure with the lowest energy as illustrated in figure 1 and 2. That figure 1 and 2 is shown on your screen. In first figure, you can see the various shapes of the say molecules, and in second figure, you can understand it's a three-dimensional and two-dimensional structures. So, in the VSEPR model, the molecule or a polyatomic ion given an AXMEN designation, where A is the central atom, X is the bonded atom, E is a non-bonding valence electron group. Usually, a lone pair of electrons and M and N are the integers. Each group around the central atom is designated as a bonding pair or a lone pair. From the bonding pair and lone pair interactions, we can predict both the relative positions of the atoms and the angles between the bonds, called the bond angles. And using this information, we can describe the molecular geometry, the arrangement of the bonded atoms in a molecule or polyatomic ions. And you can see here again the various shapes and their geometries. All these things are given, and whenever we are predicting all these things, the VSEP are having some procedure which is summarized as a in a following manner, that is to draw the Lewis electron structure of the molecule or a polyatomic ion. First of all, we have to draw the structure, then determine the electron group arrangement around the central atom that minimizes the repulsion, assign an AXMEN designation, then identify the lone pair, bond pair, or the bond pair interactions, and predict deviations from ideal bond angles. And finally, describe the molecular geometry. So, you can illustrate with the use of this procedure with several examples, and beginning several examples beginning with atoms with two electron groups. In our discussion, we will refer to figure say 1, 2, and figure 3, which summarize the common molecular geometries and idealized bond angles of molecules and ions with 2 to 6 electron groups that are summarized in our figure number 3. So we stop here, and later on we will go for the in the next lecture we will relate it with another topic, or we can say the geometry.